Hi class, the first lab that we have other than the techniques lab is the determination of melting point, and this is something that you would be doing on a very regular basis each time you develop for yourself, each time you carry out a synthesis reaction where your product is a solid product. You can determine the melting point, and since a melting point is a physical property that basically tells you how pure a certain compound is. So you can discuss the purity of a solid sample, purity of a solid sample by determining the melting point. The whole idea here is that if your sample is impure, then you never get a sharp melting point, you always get a range of melting point. And so what I mean by that is that the entire morphology that one expects when crystal tends to shrink, sag, and melt, that entire process, which otherwise for a pure sample is supposed to take no more than 0.5 to 1 degree Celsius, if your product is an impure sample, it's going to take like 5 degrees Celsius or even as high as 20 degrees Celsius, depending on the amount of impurity that is present for that particular sample. So what you just heard is that impure samples will show you a range. Impure samples will give you a range of melting point, and the other thing that you should realize is that when you take a melting point, and if the sample is impure, then your melting point is also going to be lower than expected. Lower than expected. What do we mean by that? Essentially, when you carry out, provided you're taking all the precautions that are necessary for that particular experiment, when you carry out the experiment, you're going to expect when I say lower melting point, again, depending on the amount of impurity, it can be as low as 10 to 20 degrees to as little as maybe just about 5 degrees or 2 degrees. So you have to keep an eye on the literature value and report what you got. Now, how do we prepare a sample? How do we pack a sample? That's the next thing. As the instructions tell you that you're supposed to take about 100 to 200 milligram sample. Now, you don't have to necessarily weigh out 100 to 200 milligram sample. You can just take 1 to 2 microscopula full. Microscopula full on a watch glass. So even though the instruction says that you should use a filter paper, if I were you, I would not. If you look at the student notes, it says clearly, do not use a filter paper, use a watch glass. And the reason for that is that a filter paper, the paper fibers can contaminate your sample and they can mess up your reading a little bit, and we don't want any contamination for that matter. So if I were you, between you and your lab partner, what I would suggest, since we are going to do 4 samples, what you should do is you should divide the work, and each of you should do 2 samples at least, so you get a good feel of what you're doing with the melting point. Now, in order to again prep the sample, what you do is you take a little bit of the sample and you put it on the watch glass, and you would use the back of the spatula. So here is your spatula. You can use the back side of the spoon and simply use your index finger on top of it to press gently to make sure that there are no big lumps or crystals that are still present. We have taken the time to powder this, but this is just to make sure that it is as powdered as possible. I would suggest that no more than 100 to 200 milligrams on a watch glass. Use the back of the spatula to powder powder, and then start filling in your capillary tube. Now, the whole idea of powdering, the whole reason for powdering rather, is that let's say this is your capillary tube. If this was not powdered, what would happen? You would see these differently shaped and different sized crystals. Notice there's a lot of space. This is empty space, which has nothing but air. And so since it's not uniformly packed, the heating is going to be non-uniform, and the air in between is going to expand while the heating takes place. So you will see some bubbling, you will see, some weird observations, some strange observations which you otherwise are not supposed to see. So when you keep this completely powdered, you minimize all of that. So what happens is you have very teeny meeny particles which stack upon each other very, very well. The stacking occurs pretty much the same way as you might envision, how they place the oranges or the apples in the produce section that you want to just kind of tip on the side. And this exactly looks like that. So you are minimized, you're using up majority of the volume of the space. So the excess has been minimized. And so for that reason, there is minimal amount of air, and your reading is going to be a lot more uniform for that matter. So what you will do is you will take the capillary tube, which is sealed on one side. It is sealed on one side, and it has been pre-done for you. So all you have to do is use the open end and just kind of rotate that on top of the sample. And after you rotate it a couple times, you will see that a little bit of the capillary tube is going to get about 2 to 3 millimeter of the sample, and that's your aim that you need to fill in your capillary tube. So you would then invert the capillary tube, and you will see that your solid is going to essentially fall into the bottom of the capillary. Tap a couple of times on your bench top, and we are going to provide you long glass tubes. So it's a good idea to allow the capillary to fall through that on the bench top, and you do that maybe 3 to 4 times. And the reason why you would want to do that is basically because that way you would tighten the packing, and the amount of air that is present in between the particles, that's going to be minimal. And again, so that's going to give you a nice uniform heating. Your readings are going to look much, much better, and you won't have any air that will interfere with your reading. Now, when it's time to get your data, what is it that we have to do? You are going to run, essentially, like I said, 4 samples. Okay, everybody has to run beta-naphthol, benzoic acid, the mixture of beta-naphthol and benzoic acid, and you have a choice to either pick urea or acetanilide. So between those two, it doesn't matter which one you pick, but you have to pick one or the other. The rest 3, beta-naphthol, benzoic acid, and the mixture, that everybody has to run. Now, what is it that you will do? Like I said, between you and your lab partner, you have to run these 4 samples, and you have to give me 3 readings for each of those. The first reading is going to be a fast reading, and the remainder 2 are going to be slower readings. So what is a fast reading? What is a slow reading? Realize that when it is a fast reading, essentially your heating the heating pad, the heating block in which you would have inserted your sample, that is going to be heating at a very elevated, at a very fast pace, because of which it's going to be non-uniform, and usually the readings that you get because of that sometimes are higher as compared to what the real literature value is. So it starts to melt at a lower temperature, but overall the value comes out to be higher, because by the time you take the time to see the temperature on the thermometer, 2 or 3 degrees have already passed. Still, nevertheless, we call it a crude reading and we still take it, because that way we are getting an idea as to what is the range, the generic range in which the melting is going to take place. So for instance, if I wanted to determine a certain compound that melts at 100 degrees Celsius, and I just wanted to get a ballpark value, whether it's 100 degrees or 200 degrees or what, I could carry out a very fast, very quick heating, in which I'm going to heat it at, set it so like I said, the shrinking, sagging, and melting. So like I said, the shrinking, sagging, and melting has to take place within the 0.5 to 1 degree Celsius, and so you have to make sure that your samples are pure, nicely packed. These are some of the precautions you're supposed to take to be able to get a good data on this lab. Now, let's see what we are going to do with this. So you will prepare your sample. You will have your observation table is what I'm giving you right now. The first column should say compound. The second column should say true value. So if you're giving me true value, you must cite it. In order to follow any citation, you should follow the link for ACS that I provided on Blackboard. And then there'll be a fast reading column, there'll be a slow 1 reading column, and of course there'll be a slow 2 reading column as well. Now, let's say you took, the first sample that you took was beta-naphthol, and you find out the true value, and you run the fast reading. So that's the crude reading, for which I told you that you should set it around 6 to 7, so that you basically get a ballpark estimate, in terms of how much the temperature is going to be. What you're then going to do is you're going to slow it down. So you're going to slow down and now do a slow reading for the same compound. In order to do a slow reading, what you will do is you will cool your melt temp approximately 30 to 35 degrees lesser than what the melting point was. So let's say in the crude, your melting point came out to be 100. So fast reading gave you a value of 100. That means you're going to cool it down to around, 65 to 70 degrees Celsius or so. This is just the safe region that you are cooling it down, so that when you put your 2 capillary tubes, they don't melt instantaneously. You do want to again heat it, and heat it nice and slow this time, so that you're able to get your measurement. Now, I do allow you to set up, since your melt temp can hold up to 2 capillary tubes, double L. So one of them is a thermometer probe. That's a thermometer probe. And then there are 2 other spots. You can put both of your slow readings together at the same time and do the slow heating. For slow heating, you should maintain no more than 2-degree change per minute. So it has to be very, very slow. And as you go, usually on the blue melt temps ballpark, you should not go past like 3. Somewhere around 2 to 3 would usually give you that. But depending on the kind of melt temp you have, you will be able to make your call depending on your your sample. Now, I would also recommend that instead of relying on the digitemps, you should actually put the traditional thermometer. That always works better. The digitemp, if it's low on battery or something's odd about it, it's going to give you a weird reading. On the other hand, the traditional thermometer always is more reliable as compared to the digitemp. So if I were you, that is what I would always place in the thermometer holder, which is that cylindrical aluminum spot that you can place your thermometer in. And then carry out your slow reading. So that's what you're going to fill in here. And you're going to do this 4 times for the 4 samples that you're supposed to take. And like I said, you should divide your work into both you and your lab partner, since you're going to be working in groups of 2. You should essentially carry this out in such a manner that everybody gets an opportunity to run at least 2 samples. So if tomorrow your lab partner didn't show up, you still would know what has to be done for a melt temp. This is probably by far the only time you're going to take a fast reading. Usually later on you probably will not even be taking the fast reading, and directly you'll jump into the 2 readings for the slow reading. Now, in your observation table, you should also include an average. Let me talk about that a little bit. Usually, like I said, the slow reading would not vary the whole thing of shrinking, sagging, and melting. That should take place within like 0.5 to 1 degree. So even if it's a range that, let's say it was 100, so suppose it came out to be 99.5 to 101. I want you to record the entire range over in your observation table. Please do not try to take an average, okay? And so let's say you did the slow reading once, and that came out to be 99.5 to 100, and the second one came out to be 99 to 101, suppose. Okay, now average does not mean that you're going to take an average of the low and the high. No, you're going to take the average of the 2 lows and the 2 highs together and report that as a range still. You're not going to take an average and report like one single number, but rather still a range. Let me be very clear about that. If you don't do that, you are going to lose points in the way you are recording the data. So if you have any questions, feel free to ask me about that. After you have done this for the 4 samples, I just talked about the observation table as well. As far as the conclusion for this lab goes, like I said, the conclusion is what you expected to complete, to accomplish in this lab. So the aim of this experiment was to determine the melting point of known and unknown compounds and mixtures. So let's say that was the aim. Essentially, you have to tell me if the aim was satisfied or not, achieved or not. So in your conclusion, you must give me the average melting point ranges of all the samples you ran, along with the literature value, and that too hopefully would be a range, to determine percentage error. So percentage error can be determined by the difference between the true value and the experimental value divided by the true value times 100. So you don't have to do that for both the high and the low. Let's say your average came out to be the data that we had. It was what, 99.25 to 101. Suppose that was your experimental data, and the value that we know from literature, that happens to be maybe 100 to 101.5. Suppose, okay? So what you'll do is you'll find out the difference between the low divided by the true value, which is 100, times 100, and you'll write that as the percentage error in recording the data. So conclusion, we'll talk about all of this, and you should do that for all the 4 samples. You can tabulate it if you want to, that's okay, or you can write it in words, but that'll be it.